In the second part of this presentation, we'll look at different ground source heat pump system types. First of all, with the heat pump itself, we can have different strategies. For instance, do we use a heat pump that only has on-off control, or do we have a heat pump or heat pump system with frequency control? Another consideration is whether we will have a hybridization with, for instance, a gas boiler or a chiller, or backup heating with an electrical element, to give an example. Another consideration is the type of building. With large buildings, utility or tertiary buildings, you may need low temperature cooling, which can be supplied by the ground source heat exchanger or ATES system, the aquifer thermal energy storage, so basically closed loop or open loop systems. If we have a single family house, we would normally select a single small collective closed loop system ground heat exchanger. For instance, a single borehole or 2 boreholes or 3 boreholes or horizontal heat exchanger. Looking at multifamily houses, there are different opportunities like apartment buildings with a central heat pump system that can use a single collective ground heat exchanger borehole system or an open loop ATES system. We can have individual heat pumps, every apartment with its own heat pump that use together a single collective ground heat exchanger or ATES open loop system. And we can have the situation where all the apartments have their own heat pumps, so again, individual heat pumps, but every apartment is connected to its own small collective ground heat exchanger. And then we can even mix it where several apartments together use a couple of ground heat exchangers, but more small collective systems are used for the whole apartment building. So how do we select the emission system? Well, the first important fact, of course, is that the efficiency is very much dependent on the temperature and better the temperature difference between the cold side and the hot side. And different emission systems have different temperature requirements. A heating system using radiators, for instance, will need a flow temperature between 45 and 70 degrees C. 45 degrees C will probably need oversized radiators and forced convection using little ventilators on the radiators themselves. If we have a fan coil unit to the ceiling, then we can do heating, let's say, between 40 and 50 degrees C and cooling between 15 and 20 degrees C. If required, even lower temperatures are possible, but of course we need to take into account then condensation. On an underfloor heating system, the heating will be between 32 and 40 degrees C, and the cooling will be 20 degrees or a little bit higher to prevent condensation on the floor. And for an air handling unit, it depends. We can have, again, heating at 40 to 50 degrees C and cooling, depending on whether we want to do dehumidification or not, somewhere between 6 and 15 degrees C. So important for the selection of the emission system is the temperature that we need and the required flow temperature and the adjustability of the system in part load conditions. Integration with the building can be done in many, many different ways. We give a few examples in the following slides. Some key points are the flow for the heat pump, which needs to be constant or variable. For instance, on a frequency-controlled heat pump, you can have variable flow regulated on delta T on the evaporator and condenser, but on an on-off heat pump, you will virtually always need constant flow on both the evaporator and the condenser. At the same time, the building may need a variable flow, which is important to prevent high return temperatures in cooling or low return temperatures in cooling or high return temperatures in heating. So we need to decouple the heat pump system from the building system, hydraulically decouple those two systems so that each can have their own flow rate. If we have decoupling, we usually have a buffer tank or a low-loss header. We want to prevent mixing there as much as possible because mixing of temperature destroys the temperature quality and reduces the efficiency of the system. Another aspect that we need to take into account is that we want to have a high temperature difference on the building circuit. So we need basically variable flow for part load conditions with control on return temperature. If we push out 45 degrees on the heating side and we get back 44.5 in part load conditions, the heat pump cannot function. We need a return temperature between 38 and 40 degrees for the heating system to function. And with hybridized systems, this becomes even more important. Make sure the heat pump has authority and not that when the gas boiler comes online, the return temperature increases, or when the chiller comes online, the return temperature decreases very quickly. So the first example is very simple. We have a heat pump system coupled to the ground, either open or closed loop. We have a domestic hot water tank where we generate heat for the domestic hot water supply, and we have a fairly simple underfloor heating cooling system. The domestic hot water tank can have a backup electrical heater, also used for increasing the temperature for Legionnaire's disease protection. And on the ground side, the hydraulic side, we can see some valves and a plate heat exchanger for a free cooling loop. The plate heat exchanger is required to prevent glycol or other antifreeze mixes being circulated over the building system, and the 3-port valve is used to, let's say, mix that temperature, bypass the heat pump, and mix the temperature to the required temperature on the underfloor heating side, keeping it above, let's say, 20 degrees. Obviously, a frequency-controlled source pump can also play a role in this type of regulation. Slightly more complex example is where we have a heat pump decoupled from the building system. The building system has its own circulation pump circulating over the tank, so the tank can be, let's say, charged with heat or charged with cool by the heat pump system, and a different flow rate can exist on the building side, where then the underfloor heating has its own little circulation pump with a throttling valve to control the temperature, the emission to the space on the underfloor heating. We can also have an air unit, a fan coil unit, again with a throttling valve to control the temperature in part load conditions. In both cases, the return temperature will be low during heating and high during cooling to allow the heat pump to function properly. On the far right, we can see an air handling unit with a bypass valve, a 3-port valve, where the capacity on the fan coil unit is controlled by bypassing part of the flow and mixing that into the return to the storage tank. In this case, we'll get a small temperature difference on the building loop, which is not recommended. A further example is a bivalent, a hybridized system where we have a boiler in the loop. In this case, the heat pump functions as a preheating for the boiler that can then inject more heat into the system for the underfloor heating system or the air handling unit or the fan coil unit. Here, again, it is important to make sure that the return temperature from the system is low enough to allow the heat pump to function